Hello, my name is Andrew Lee, and I'm here with my colleague Rudi Stouffs, and we want to talk to you about our shape grammar implementation, which has two interfaces, and from which we learned quite a lot about how users use shape grammars. So the technical background, we're just going to give you a very brief overview. The formalism itself was developed in 1972, and then implementations have come slowly but surely. We had a 2D implementation, and then a 3D implementation, parametric implementation, and then more recently also advanced objects such as surfaces in 3D. In terms of the interface, Tapia's was the first to have a visual interface, which we think is relevant because that's the whole point of shape grammar, is to have something that is visually immediate. And then both I and Graziani Economou have also continued in this line. Now, our implementation is built for Rhinoceros 3D versions 5 and 6, both Mac and Windows. And it's got three parts. One is the back end, which is the part that does all the work, and two front ends, one visual and one technical. The back end itself is where all the work is done. As I said, it's called Sortle.gi, and it really is just a general purpose shape grammar interpreter, and it was developed in Python. The visual interface is one of two front ends, and what we'll do now is show you a video of how to make a new grammar in a new Rhino document. So it's going to add and subtract squares, and which is pretty simple, but it just shows you how it works, and it also handles emergence. So here we have a new Rhino document, and we're going to initialize it. And then what we do is we will draw the initial shape. It's going to be a square. And we need to blow it up because it needs to be not a polyline, but separate lines. And we will put that on the shape 0 layer. That's the initial shape layer, which was created when we initialized the document. Now we're going to create the parts for the rules. It will consist of two squares. And we're doing this on the near side of the y-axis. That's reserved for the user. The other side of the y-axis is reserved for the system. So now we're creating the rule. The left shape, we've specified the left shape and its reference point. We've specified the right shape and its reference point. And you can see that a rule was created on the upper left with the arrow in between. Now we're applying a rule, and you can see we got 4 new shapes. The rule was applied in 4 different ways. And we're going to apply it again. And now it will act on the emergent square. And so you can see we've got lots more new shapes here. Now here we're creating a rule, and we're going to do a delete rule, a delete square, and we just specify the left shape and nothing for the right shape. We get a new rule, and we can apply it, and it will find all of the emergent squares and delete them. And so there you have about 7 possibilities. Okay, now you can also, because the grammar is in a Rhino file, the Rhino file itself serves as a storage, it stores the grammar. So you can open an existing file and use it. And so here's one. It has the rule. The rule is already part of the document. And this shows the generations of, this is the 3D Sierpinski gasket, and starting from the initial shape and successive generations as we apply the rule. So you can see this also works in 3D and has emergence as well. This is a technical interface, which Rudi will tell you more about.
Thank you, Andrew. So this is a Grasshopper plugin, and it's technical in the sense that you cannot just draw the rule like previously, but you actually have to build a small grasshopper model to define and apply a rule. And it comes in with a number of different elements, but I'll just mention the most important ones. So a shape is basically a Rhino geometry, except that you can add textual attributes and textual descriptions. A rule, of course, is defined by two shapes and can apply to another shape. And descriptions are defined by Steiny to allow you to add design intent or other constraints to rules. Next. The system supports two matching mechanisms that can be approached through this interface. One applies a rule under a similarity transformation, the other one under a topological-associative transformation. Next. Let's first consider applying a rule under a similarity transformation. This is an example from Steiny, in which there is a rule that takes a square and it inscribes a rotated square into this. And this rule applies under to any square, whether irrespective of its size, its orientation, or its location, such that you can keep on applying the rule to the latest created square to create these kind of patterns. Next. This is a bit more of a complicated example using curves, or specifically quadratic Bézier curves. It's an example from Jowers, and it actually doesn't use scaling, but it does use translation, rotation, and reflection as transformations. Next. Now, the topological-associative transformation is a mouthful. Basically, it's a graph-based, and it allows you to match arbitrary polygons onto arbitrary polygons of the same number of sides. So quadrilaterals onto quadrilaterals, triangles onto triangles, etc. Next. And so here's a very straightforward example also from Steiny, in which you have rules that take a polygon, either four-sided, three-sided, or five-sided, split it into two polygons, smaller ones, also 3, 4, 5-sided, to create ice ray patterns. But it just takes polygons and splits them into polygons. Next. And this is an example to show that you can also do this in 3D. Here you have a rule, again, applying to quadrilateral that kind of scales this quadrilateral or reduces it to a rectangle and then extrudes the last figure. And notice that the extrusion, it's not always the same. The height of the extrusion is actually related to the ratio between the area of the original polygon and the area of the the extruded polygon. And that relationship is embedded as a description into the rule. It's kind of hard to see, so let's do another example. Next. This example is clear, so there's this description. This description has basically a list of possible labels from fish pond to terrace to etc. And then there's a function, a random function, which picks a number between 0 and 9. And there's an item function, which applies this random number to this list to pick a random value from this list. And it will assign this automatically to each section of the design that is being generated. Next. So considering the technical interface, there are advantages and disadvantages. Most obvious maybe is a disadvantage requiring extra work. It could distract from the design action. The advantage, of course, is if you're already using Grasshopper, it offers many extra opportunities for exploration. And the best example, next, is maybe this one by Simon Prokop from a workshop that was held at the ICADC Gradi conference in 2019, in which he basically explored hundreds of shapes using the the plugin as well as other Grasshopper components and plugins. Next. Thank you, Andrew.
Okay. So we took advantage of as many opportunities as possible to get people to use our implementation. So in 2019, these are 3 workshops that we tried it out in. And one of them, the one in National Yunlin University of Science and Technology in Taiwan, it was 8 days long, and we had really great facilities for fabrication, laser cutting and 3D printing. And what you can see here is that the students, the participants made many, many objects, and we found that this was really important for them as part of the design process, not just for the 2D objects on the left, but especially for the 3D objects on the right, because it's really hard to really understand a 3D object just from a screen representation. So we found that this was really important, and this was actually a main part of the 2 takeaways, the 2 lessons that we learned from our work that we're reporting now. One is, what is the relation of shape grammars and the interpreter in the larger design process? In other words, we have these designers using these tools, but how do they use it? And fabrication being important is one part of it, and it's an aspect of the fact that designers are pragmatic. Designers are interested in design. They're not interested in technical shape grammar stuff the way we are. That's why we're developing the tools, but we want them to use it. The other big thing that we realized we need to think about is the relation between these 2 interfaces. We have one that's visual and one that's technical, one that's immediate and intuitively obvious, and one that's technically powerful. Now, one might say, well, the obvious thing is, well, just combine them and, you know, get the best out of both in one package. But what we noticed from users is that designers really, they took very quickly to the visual interface, and they weren't really interested in any of the more complicated things. And on the other hand, for the technical interface, the people who got the most out of it were the people who were already quite technically proficient, who knew how to use Grasshopper, who knew some of the more technical aspects of shape grammar. And so we think that actually we may need to, each kind of interface may have its own purpose and its own type of user. And, you know, so it's not obvious that the correct thing to do is to combine these. In any case, what this means is that we do need to get more people to use it and learn more from their experiences. So thank you for listening. If you're interested in trying these out, these are the places to look. Thank you very much.